Today I'll talk about Bayesian regression. It is part of my series of lectures on machine learning. This is my lecture outline. First I will give introduction, then I'll talk about assumptions of Bayesian linear regression. Then I'll talk about advantages and disadvantages of Bayesian linear regression. Then I'll talk about steps of Bayesian linear regression. Then I'll talk about mathematical basis of maximum likelihood estimator, Bayesian approach to regression, Bayes regression, and Gaussian process regression. And finally, I will give an example in Python code of Bayesian regression. So Bayesian linear regression is a parametric Bayes net process. The aim of Bayesian linear regression is not to find a single best value of the model parameters. Bayesian linear regression determines the posterior distribution for the model parameters. This is achieved using the concept of normal distribution and Bayes theorem. This I will make clear in my topic on mathematical basis today. Bayes theorem provides us tools to update the belief in the evidence of new data. Bayes theorem describes the conditional probability of an event based on data and prior information about the event. So the relevant techniques related to Bayes theorem include Bayesian linear regression, the topic of today's lecture, Bayesian logistic regression, and Bayesian neural network. So assumptions of Bayesian linear regression. Bayesian linear regression model is a linear model. The variables should be independent and identically distributed. There should be homoscedasticity and likelihood should follow normal distribution. Advantages and disadvantages. When the data has too few or poorly distributed data, Bayesian linear regression is more appropriate method, and it is well suited for online learning as opposed to batch learning. Whereas Bayesian linear regression is not worthwhile if there is lot of data available. In such a scenario, usual linear regression will be more efficient. Steps. So this is the summary of steps of Bayesian linear regression. First of all, we specify priors of the parameters. Then we create model mapping from input to output training data. Then we use Markov chain Monte Carlo algorithm to draw sample from posterior distribution. And we use one of these two methods. One is Gibbs sampling, the other is Metropolis Hastings sampling. And finally, the algorithm converges. Then mathematical basis of maximum likelihood estimator. First of all, normal distribution. The probability density function of normal distribution is given by this formula, where this is the observation and this is the mean. So distribution of outcome variable. So if y is outcome variable and it is regressed on input variable, that is x, and this is matrix of x variables. This is the vector of parameters which we need to estimate, and these are the error terms. So y is equal to w transpose x plus error. So y minus w transpose x is error. We already know that distribution of error terms, this error term is normal with mean 0 and this variance. So error terms are normally distributed, and this is as sigma square. So sigma square, we use beta inverse for sigma square. Hence, the difference in this left hand side, the difference in the actual and predicted is also normally distributed with this variance. So y is normally distributed with this mean and variance. It can be said like that. So probability of y is again given by this formula, which is similar to the formula for normal distribution. And the sigma square is variance. So probability of data is equal to probability of y, so that we have available input data and we have parameter vector, and this is same as probability of y. We will see it later on now. So by our conditional independence assumption, we can write the joint density of the data set as probability of data is equal to probability of y, so that we have available data and parameters is equal to multiplication of probability of individual data points. So this is actually likelihood. So maximum likelihood estimator. So we have seen that likelihood is multiplication of these normal distributed terms. So log of this probability or maximum likelihood is this. So we can calculate the parameters from this maximum likelihood estimator as parameters is equal to argument minimum W, and these are error terms. The same can be represented in matrix form as vector W is equal to inverse of X transpose X multiplied by X transpose and multiplied by Y, and which is equivalent to least squares linear regression. So this is the likelihood from the data. Now, Bayesian approach to regression. So in this likelihood, we will add one more term. We will add priors for the parameters. So this is the Bayes theorem again. And we need to maximize this probability. That is probability of our vector of parameters subject to the outcome variable. And this is equal to this. So if in order to maximize the left hand side, we need to maximize this numerator. So it is as maximum of this term, and where this first term is known as likelihood, which we have seen in our previous example here. This was the same likelihood, and we used only this likelihood in least square linear regression. Now here we are using the prior term also. So this is the prior probability of our parameters. So it is normally distributed again with mean 0 and with this tau square variance. And our outcome variable is normally distributed as we have seen before. So now likelihood is given as this. Again, this is very similar to our previous example. So log of posterior proportional to log of likelihood plus log of prior. Hence, if we need to maximize this term, then we need to minimize this term, and this term include this error term as well as the regularization term. So this regularization, this sigma square divided by tau square can be written as lambda square, and in matrix form this is same as this term, and this is known as ridge regression. So in ridge regression we have the regularization term here, that is lambda multiplied by the identity matrix. So this was Bayesian approach to regression, from which we got ridge regression. Now Bayes regression. This is our topic for today. So we need to first define the prior of the parameters, that is distribution of parameters. So parameters are, let us say, normally distributed with mean 0 and variance as alpha inverse identity matrix. So this is the parameter assumption. So Bayes theorem, as we have seen, posterior is proportional to likelihood multiplied by prior. This PA is prior. So log of posterior is proportional to log of likelihood plus log of prior. This we have seen in our Bayesian approach also. Since prior is Gaussian, the posterior must be Gaussian. So for parameter distribution, probability of parameters. subject to data availability is proportional to probability of data multiplied by probability of prior. Now this probability of data is likelihood. So likelihood is, as we have seen, is multiplication of likelihood of individual data points and taking logarithms. So we got this. So the expected values of parameter is given by this term and the variance of the parameters is given by this term. So for prediction of the outcome variable from the new data point, and this is integration of this term, which is same as this term with variance of this. So this is the mathematical basis of Gaussian linear regression. Now let us see about Gaussian process regression. So a kernel-based fully Bayesian regression algorithm is known as Gaussian process regression. A Gaussian process is written as this term with this mean and this variance. This is actually covariance. So with a mean function this and a covariance function this for any data points. So Gaussian process is written as this, where the error term is of course normally distributed with this variance and this for some valid covariance function this. So this is Gaussian process regression. And similar to our previous approach, we can solve and we can predict the values here like this. So this is prediction of the mean and this is the predicted variance. So now example in Python code. So these are the libraries which we import. We import pandas for data frame. We import NumPy for array and mathematics. Then we import California housing data set. Then we import train test split library. Then we import linear regression. This is the usual type of linear regression. Then we import Bayesian ridge and ARD regression. So Bayesian ridge and ARD regression are the Bayesian linear regression. And this is one of the metric which will use mean squared error and this is for plotting. So this is our database. So it includes these input variables and this is the target variable. Then this is train and test split. Then this is the coding for linear regression and these are the coefficients for our input variables and this is the score. Then this is Bayesian ridge regression. This is one of the Bayesian linear regression. This is the vector of the parameters and this is the score or mean squared error score. And this is the ARD regression. Coding is very similar and this is the vector of parameters and this is the mean squared error score. So the results of all these three are very similar because our data was suitable for all these three. But there are instances when our data is suitable for only Bayesian regression as we have seen in our initial slides today. This is all for today. Thank you very much.